Oh, hi there, gang. I was going to film this video outside today, but it turned out to be a cold, blustery day and really not great for filming. So here I am inside filming something which is very, very similar. And the plan for today was going to be a cool bike ride. But anyway, that didn't work out. But I will show you the cool bike I was going to use today. Here it is right here. One of my coolest ones. Now you're probably laughing. Although it is quite a cool little bike, actually. I'm quite proud of it. That's original paint, and that's a Whirlick, built in Preston, Ontario, not far from Brantford. It's a nice one. Now, would I have actually ridden this bike today? No, I probably wouldn't have, although I have in the past. And that question is, why wouldn't I have ridden it today? And of course, the answer is quite simple. You can't really go that far or all that fast on a tricycle. But here's the interesting question. Have you ever thought of why that is? Why can't you go all that far or all that fast on a trike? Well, the reason really is quite simple, and I'll show you how it works. A tricycle is a very simple design. It might make you remember your grade 2 simple machines unit, actually. These are all levers and wheel and axle. In this case, the pedals act as levers, and they're connected directly to the axle of the wheel. And the axle of the wheel is connected to the outer portion of the wheel with these spokes. So it's really just one big unit. And as I press my pedals down and up, it rotates the wheel around one time. So down and up is one rotation. Down and up is one rotation again. If I want to go faster or farther, I have to start turning quicker and quicker and turn as fast as I can. Now, how fast can a person actually turn the pedals of a bicycle? And the answer is, surprisingly, not that fast, right? You would start to turn and start to get quicker. And you would get up to about 1 revolution per second. That's 60 revolutions a minute. And that's about the most comfy. 1, 2, 3, 4, 5. That's a comfy rotation. A good cyclist can go a little faster than that. They can go about this fast. That's about 100 revolutions a minute. Well, that's a little bit uncomfy. But if you try to go faster than that, of course your feet fly off the pedals and your knee smacks into the handlebar, and then you're crying, and then you go home and you need a lollipop. So basically, you're not going to go all that far or all that fast on a bicycle like this. What's the reason for that? The reason is a tricycle does not have gears. So perhaps a bicycle like this would be a whole lot better. So let me just roll this one into view. There. Now a bicycle like this has gears, and the gears will allow you to go much quicker and much more simply for a longer distance. Now I know some of you are getting all grumbly and complaining already because you say to yourself, well, wait a second. We studied gears in first term, and we studied them fairly extensively. We even built things out of gears, right? I don't see any gears on that bike. Well, in a way, you're right about that. I mean, the gears we studied look something like this, right? You might say to yourself, I'm interested in seeing something which looks like this. You know, that's like a toothed wheel, and it's beside another toothed wheel. And as one toothed wheel turns, it causes the other toothed wheel to turn simultaneously. And that is a meshing set of gears, right? So that's what you're accustomed to seeing. In this case, you don't actually see that. But actually you do. Surprisingly, these are not 2 gears. These are actually 2 chain rings from my collection. And they're not intended actually to come into contact with each other. These 2 chain rings are intended to carry a chain across these teeth. Basically, pull a chain around the teeth as they rotate. And as the chain comes off them and the chain extends, as far as you want to extend it, it extends to a second chain ring, which is also simultaneously pulled by that chain. So both are moving each other the way gears do, but they're just moving each other in a slightly different way because the chain is helping them do that. Now here's one thing that's kind of cool. Look, if you look carefully, you'll see that these are marked. This is my Zeus 52 tooth chain ring, right? This is my Zeus 51 tooth chain ring. Tricky. So this chain ring actually has 1 fewer teeth, than this one. What does that mean? Remember your term 1. If you're if you're rotating a larger gear against a smaller gear, what's going to happen? Well, if you're rotating a larger gear against a smaller gear, that smaller gear is going to turn ever so slightly faster. Remember that? Works the same way on a bicycle. Now, let me show you that on this bicycle. Come on over here, please. Now, on this little bicycle, you'll see that we have a number of different... Oh, careful not to block the light there, camera person. That's one much better, thank you. On this bicycle, you'll see we have a number of different chain rings. We have the chain ring on the front right here, which you can see if you look inside here. It's sort of behind this plastic cover to prevent little kids from getting hurt. But there's a little chain ring inside here with the same teeth as the one I just showed you. And it's carrying the chain around this little wheel. And then back here, we have a number of different little chain rings of different sizes. Now, all I need to do is take a little piece of tape like this, and I will show you that that action of the different sizes makes a huge difference. Look, I'll take this piece of tape and I'll tape it to the very, very top of where this little bunch of cogs is now sitting. So you'll see now that the pedal is, there we go. The pedal is in the up position. And this chain ring now is in the up position. Now, if I start to pedal that chain ring, you'll see something kind of cool happens. I start to turn my pedals, and now I've turned my pedals, and I've turned my pedals to the point that the first pedal here is just coming to the very bottom of, oh, look at that. Now, isn't that fascinating, right? I've turned my pedals only 1/2 turn, or approximately 1/2 a turn. And I've already turned this little cog around 1 time. Interesting. Which means the back cog is turning almost exactly, there it is. I'm back up at the top and there it is. Which means with the chain sitting on this front cog and this back cog, this whole assembly is turning around about 2 times for every rotation of this. Want to see it again? There's 1 and there's 2. Fascinating, right? By the way, that's the math. And there is going to be some math that's associated with this. If this were a 50-tooth chain ring, and this was a 25-tooth chain ring, that would be exactly half. And of course, that would mean that if I turned this once, this would turn twice. And if I turn this 100 times, this would turn 200 times. But that's not only it. Watch. If I change my chain now to the very, very bottom, down to this little itty-bitty cog at the very, very bottom, you'll see that I can get some amazing differences in speed. Okay, there. Now let me see if I can get this worked out now. Let me get my piece of tape at the top again. Right there, perfect. Okay, I'll get as close as I can. There, perfect. Now watch this. I've now changed it so that I've put the chain on the very, very smallest and lowest cog. I don't know if the camera can see that. Can the camera see that, camera person? Mm-hmm. Okay. Now I'm going to turn the pedals back again. Now watch, I'm starting from the top. Here's where I'm starting from, and watch that piece of tape. So I turn down, and holy crow, this time I've turned only 1/4 of the way around. And there's that tape coming up. There I am now at the bottom. There's tape coming up again. And as I bring it up to the top, the tape comes up again. Look at that. That's incredible, isn't it? Which means I turned the pedals around 1 time, and I turned the back cog 3 times. Fascinating, isn't it? Now you might say to yourself, who cares? It's the whole big game, which you can spin faster? No, because if you think about that, it's not happening in backward, it's not happening in reverse, it's happening in forward direction. What it means is, in this gear right here, which is my top gear, if I am turning my pedals fairly slowly, my back wheel is turning really remarkably quickly. Like, that's a slow turning of the pedals. Imagine how slow I'd be going on my tricycle. But the back wheel on this bicycle is going remarkably fast. Now, question. Can I actually use that gear at the very beginning of my ride? No, I can't. I've got to start, actually, the same way I would on the tricycle. I will start using a very, very simple gear. The same way the tricycle would be. Almost the same. Put it back up into first gear, excuse me. Okay, it's hard to do without an assistant. And my assistant is filming right now. I need a second. There we go. Okay, that's first gear right here. Now, first gear, right, is a lot easier for me to push. It's almost like the tricycle because I've got a very, very, very different relationship between my front cog and my back cog. They're both quite large, which means they're going to turn about at the same speed. So if you notice, if I'm turning my pedals at a normal speed, my back wheel is going fairly slowly, the same way a tricycle would. But as I start to speed my feet up, and my feet get quite quick, and I say, oh, I can push harder, but I can't push any faster. Now what I want to do is, I want to slow my feet down, but speed my back wheel up. And as I go faster and faster with my pedals, I want to do the same thing. I want to slow my feet down, but speed my back wheel up. And as I keep on going, the same continues. I slow my feet down, and I speed my back wheel up, which means I'm going faster and faster and farther and farther. And that's why this bike is a much, much better proposition at taking for a long trip. It's even making me tired holding it up off the ground and pedaling. Okay, now look, two things come out of this for us, okay? First of all, I'm gonna have some mathematics for you that will allow you to investigate this relationship. It's actually, it amounts to a division problem. How many teeth are here and how many teeth are here, which means if it's a larger one on the front and a smaller one on the back, if I turn this one once, how many times does that one turn? So the math is all based on that. It's division and multiplication. But also, there are some practical aspects to this. And one of the practical aspects is how it really works out in real life. How are gears used in real life vehicles? So if you're good with your math and you do well on this, your prize is I will take you for a little ride on one of my cooler bikes, okay? And we'll use the gears on that one. So if you do well on this, you can go on to your second video, which is the prize for you, which is a ride on one of my cooler bikes. And that's the end of my video.